152 to chapter 15. So that means you've got several homework assignments out right now, 13, 14, 15. Exam 3 is still for me to work on. Quizzes 5 and 6 coming up out there, May 12th, May 19th. Reminder about activity 1, that's due May 21st. The withdrawal date, May 8th. And all these things, come see me. Let's talk about it. That's office hours, Zoom. We can have these conversations. So I want you to see on the schedule, I actually have 2 days designated for chapter 15 in the schedule. However, this is a very short chapter. It's going to be 1 day of slides. That means you've got a nice buffer to get caught up on all of this. So homework, go through the notes. Because if you look, there is 1 chapter remaining. That's chapter 12. After this chapter 15. So this chapter is a really interesting chapter. It's called Equilibrium. We saw a little bit of it in chapter 14 with the acids and bases. Equilibrium, you can think right away, double arrow. But really, if you plan to stay in general chemistry at Miramar, Chem 201, the theme of that whole semester is equilibrium. You see equilibrium in many different ways. So this chapter right here is just an introduction to equilibrium to really start some of the foundation for a much bigger topic later in the semester, or later in the curriculum for Chem 201. So chemical equilibrium is what we're focusing on, and can't see it here very well, but I'm circling the double arrow. Remember, this is going both directions. Typically we think about a reaction. Well, you've got some A, and that A is going to turn into B. Well, what this is saying is just like traffic goes one way and then it's coming back, B can also turn into A. So what you have is a combination of some A present in the solution, some B present in the solution. You don't have a situation where it's just A or where it's just B. It's a mix. Okay, so this is chemical equilibrium. So I've already shown the double arrow, but that means it's reversible. So reactants form products, same time products are forming reactants. That's reversible. So both forward and reverse reactions. So if you just start with the reactants, then you form some products. Once you have some products, then they reform the reactants. This is the key. This gets really confusing because we're talking about equilibrium, so something's equal, right? Isn't that what that means? Equilibrium? Well, what's equal is the rates, okay? So the forward reaction equals the reverse or the backwards reaction. Those rates are equal, so what's happening is the amount of reactant, amount of product isn't changing because when A turns into B, guess what? B turns into A at the same rate. So it looks like nothing is happening, but really want to emphasize this is dynamic, okay? You constantly have reactant A turning into B, and you constantly have B turning into A. So that's why we say, well, let's just do it in one. That's a double arrow. That's your equilibrium situation. Rates forward and backward are equal. So let's take a look what we're talking about here. So if we think about the speed or when reactions happen, if we have a reaction with a fast rate, you see A reacts with B and goes to C. So this is really, really fast, and in just a little bit of time, it's all products. It's all the green C. Okay, if we have a slow rate, okay, of course, then you can see the reactants, purple, yellow, are starting. Well, there's a product that's forming. There's some more product that's forming. Some more product, but some reactants are left over, okay? So this is talking about rate, seeing the speed, okay? So this is really fast on the left, slow on the right, okay? So we're talking about equilibrium is the rate of the forward equals the rate of the reverse. Right here, I'm just showing you single arrow reactions. Okay, so what does this mean? Well, rate's a key part of this. So another part of Chem 201 is a whole chapter on rate and kinetics and how fast things move. So let's just talk a little bit about this, okay? So rates here, we've got reactants, hydrogen, iodine forming 2HI. And you can imagine if this is going to form, these things have to collide. So this has got to collide with this. So if you have a low initial concentration, it's going to be slow. Okay, they are not likely to collide because there's a low initial concentration. Okay, if you start increasing concentration, if you start increasing it even more, then the rate is going to go up and up. Okay, so it's just a little overview on rates. So let's get to equilibrium. Okay, remember we're getting to how this connects. Rate of forward equals the rate of the reverse. Please note this equal point, okay, this equal part, it does not mean that concentrations are equal, okay? Remember, what we just talked about, it's about the rates. The rate of forward, the rate of the reverse, that's what's equal. However, we are going to focus on concentrations in equilibrium, and we can quantify and figure out what are the concentrations, what's the equilibrium constant. So these are calculation pieces of equilibrium. So by definition, equilibrium, okay, so if we go back to A, and I'll just say that this is a gas, goes to B, what we're going to see is an equilibrium constant is governed by an equation. So the equilibrium constant is K, K is the constant, and we're going to see that it equals the products over the reactants. And there's several more rules to this that we're going to add, but I just want to start with a general idea. When you see a constant in equilibrium, it's a K. So you may recall we saw in last chapter acids and bases, we saw the Kw, and that's where the H plus equaled the OH minus. Well, that looks a little bit different. Over here, I have a numerator and denominator, base over, B over A, because those are in the gas phase. So we'll talk about the different states. The reason the H and the OH are present is because it was aqueous, and the waters on the left side of the reaction were liquids. They're not included in K. So there's some rules we'll talk about for Ks, but I just wanted you to see products over reactants, and that you've already seen this a little bit coming from a double arrow. So the equilibrium constant, just showed you it's the ratio of the concentrations, so that's molarity of products, and you raise it to the stoichiometry coefficient, and you divide it by the concentrations of the reactants raised to that exponent. And this comes from this idea of stoichiometry, mass action. If you have 1 mole of this, it forms 1 mole of that, and so forth. So that's the balanced chemical equations we've seen. The equilibrium constant expression comes from that. So if you take a look here, any reaction, so this is a general reaction. Again, I haven't put the states in yet. We'll come back and talk about the states, what's included, what's not included. But the products go up top. You raise them to the coefficient. So if that's a 2, that's a 3, you raise it to that exponent. And then the reactants are on the bottom, raise it to those exponents. So now the third example, this is a real example here. 2N2O5 gas, 4NO2 gas, and 1, remember that implies a 1 there, O2 gas. So I'm really emphasizing the states because that matters. In this case, they're all gases, so they all go in equilibrium constant. So you'll see books talk about K equilibrium. We already said KW. Your homework is going to use KC for concentration. Then you may see KP for pressure. All of this, don't get confused. We're just looking at K. It's an equilibrium constant. That means products over reactants. Raise that to the 4th, to the 1st, and see that's a multiplication there. I know it's adding here, but it's multiplication in the numerator, and if there was something else in the denominator, it'd be multiplication as well. All right, so now you go for it. Here's an example of carbon monoxide, hydrogen gas, going to methanol. go ahead and write the equilibrium constant expression is what this is called. So the expression is the K, okay? Starts with the K, and what does it equal? Things I want to point out here. First, the coefficients, that's 1, 2, 1. Those are going to be the exponents. And if it's state, so here they're all gases. We just said the rule, if it's gases, it gets included. So it's product divided by a reactant, and that's the exponent there. Okay, so what does this mean? We're setting up some K expressions, but how do we use that? Well, right away when you see K values now, you want to be able to take away some meaning. What does it mean? So let's say K equals 1,000. Okay, this is a large number, big number. Well, let's think about what is our K. Our K is products over reactants. So if it's 1,000, that means we have a lot of products. So that means the equilibrium favors the products. So there's high concentrations of products, so that's high molarity, and low molarity of reactants. Okay, well, what if our K was very small? Okay, so that's 0.0001. That's our K. Well, again, this products over reactants, that's telling us, wait a minute, we have a lot more reactants than products. So low concentration of products, that's the numerator. So if the numerator is really, really small, and then we have a big denominator, we get numbers like this, small k. So how do we get these numbers then? Okay, well, they're most easily calculated by allowing a system to come to equilibrium and then measure the concentrations. Okay, so sometimes that's easier said than done, but let's look at an example. We got hydrogen, iodine, 2HI. The concentrations are measured, and it's 0.11 molar, 0.11 molar, and 0.78 molar for hydrogen, iodine, and iodide respectively. So that's 0.11, 0.11, 0.78. So when you see a problem like this, it says for the equilibrium, so right away, equilibrium, that should be telling us K, okay? And they gave us the concentrations. What is the value of K? Well, you got to write the K expression first, okay? So very first thing, take the equation and write the K expression. So here I'm putting the product, HI is a gas, and I'm raising the exponent, that's squared here. So be careful, and remember it's the coefficient that's raised. These are just subscripts here, so that goes in the denominator. So that's hydrogen and iodine. Okay, so that's our K expression. Well, now you can see if you have the values, remember these brackets represent molarity. If you have the molarity, it's given here, then substitute it in. Okay, so that's K expression. You gotta have that or you can't do this problem. You put in the molarity, raise it to the exponent, and then both these molarities were the same, and you end up with a K. And look at this, this is a K, this is a number. Oh, this is gonna drive some of you crazy. There's not a unit here. Okay, well, units are generally not included in equilibrium. So make sure you have this number in molarity. That's got to be the unit. And we don't worry about the units of K. So it's unitless. Very different than a lot of times when you use numbers in chemistry. So let's think about the concentrations and K. So our equilibrium concentrations will depend on what you start with. Okay, so this is key. The concentrations, the molarity, depends on what you start with. However, by definition, the K is a constant. Okay, that's the point of these whole reactions, is that it's equilibrium, there's some constant. So it doesn't matter what you start with, how much you start with, as long as you have this reaction going on, it's going to form this ratio. Okay, so let's take a look at that. First scenario here. Remember, this is the same reaction. Hydrogen, iodine, 2HI. Look, we're just starting with the reactants. So there's hydrogen, iodine, there's no HI. So of course, they're going to react, they're going to form some product. The product is going to reach equilibrium, and then they're both going back and forth, and it gets to a set of numbers. Okay, so these sets of numbers, we put in, guess what? K equals 50. Well, wait a minute, look at this. You could start with just the product. So you start with just HI. Now the actual reverse reaction happens. HI breaks up into hydrogen and iodine, and it forms a new set of numbers. Look, none of these numbers are equal to each other. I mean, this is equal to one another, this is equal to one another, but all three are not equal, so that's not equilibrium. But what is the key, what is the constant, is that you put those numbers in the same expression, you get 50. Now take a look, they're all the same. Oh, they're equal. No, that's not equilibrium. Remember, equilibrium is the constant 50. Doesn't matter what you start with, the reaction will proceed. Doesn't matter what you start with, the reaction proceeds, new set of numbers, and it's constantly going to 50. That's the equilibrium constant. That's the definition of equilibrium. So now let's expand. It's talked about we're just looking at gases. Well, heterogeneous is commenting on the different phases. Okay, so if we have different phases present in equilibrium, we treat those differently. So the concentrations of pure solids and pure liquids do not change. Okay, so if you have water, that's pure water. You don't have a concentration of water. So it doesn't change. So solid liquids are not included in the K expression. Okay, we take those out in that expression. So what this means then is if you have a reaction like carbon dioxide gas, water liquid, H plus, the hydrogen, the proton, the acid aqueous, the bicarbonate aqueous. Remember, liquids and solids aren't included. So the K expression then, product times product, not the liquid, divided by the gas. That's the K. And so you see here, Kc, just products over reactants. This referring to, it's the concentrations of these substances. So this is some quantitative work that you'll see. What's the K expressions, and then put in the numbers. What's the K, or what's the missing concentration? What we'll also look at is predicting changes. Okay, so this is equilibrium has been reached. Then something happens. Okay, it's disturbed. Maybe something is added to it. Maybe something's taken away. Temperature change. This is called Le Chatelier's principle. Okay, so Le Chatelier's principle, it's just kind of fun to say as well. We're making qualitative predictions. Is more product going to form? Is more reactant going to form? That's what we'll talk about here. And this is looked at as this following. When a chemical system at equilibrium is disturbed, the system shifts in the direction that minimizes the disturbance. What this means, like before we had an equilibrium constant of 50. So if something happened and the concentrations were changed to then now that ratio is not 50 but it's 100, the reaction is going to shift to get back to 50. Or let's say something happened, you took something out, you went down to 20, the reaction is going to shift so it gets back to the equilibrium constant of 50. So that's what we're talking about here, is predicting how are things going to shift. So there are three ways we're going to look at. If you take a look here, the first one is, do we add or take away something? Okay, are we adding a reactant, removing a reactant, adding a product, removing a product? What happens if you change the volume and pressure? Okay, how's that going to affect the equilibrium? And what happens if you change the temperature? So really want to emphasize here that we've been talking about an equilibrium constant of 50. So that's what governs this Le Chatelier's, whether it goes and forms more product or forms more reactant. So number 1 and 2, they do not change the equilibrium constant. Okay, adding more stuff, taking away stuff, changing the volume and pressure does not change the equilibrium constant. However, if you change the temperature, that does change the equilibrium constant. Okay, so this is the only thing that changes the value of the equilibrium constant. So let's look at these examples. Okay, so if you add or remove a reactant or product, that's changing the concentration, so it's no longer at equilibrium. You've disturbed the equilibrium, so it shifts that it will consume a reactant or product that is added and replace a reactant or product that has been removed. Okay, so basically what this means is we have to get back to that ratio. Okay, so if we look at an equilibrium example, remember that this equilibrium equation, right away we want to write, that's an equilibrium expression, NO2, and that's squared, and that's over into O4. And this equals some number. Okay, so we have a system at equilibrium, and then we add something to it. Okay, take a look, see where we're adding. We're adding in the denominator. Okay, so equilibrium is disturbed. Okay, what happens? Well, if we add more reactant, okay, if we add more on the denominator, now this number gets smaller than the K. But the K is what governs the reaction, so the equilibrium shifts to the right, so you lose some N2O4 and it turns into some NO2 to get back to the equilibrium constant number. So how we can look at this is if you add to the left, it shifts to the right. What that means is add N2O4 and N2O4 reacts and forms more NO2. So that's adding reactant. So I would say in the class right now, for looking at this, I said, okay, I'm adding to the left, adding to the left. What happens? And you say, goes to the right, goes to the right. Okay, shifts to the right. So in this case, now adding to the right. So add to the right, add to the right. What's going to happen? That's going to shift to the left. Okay, so the reason why, we added NO2. So now we have more product than the equilibrium constant says we should have. So if you have more product, some of that's got to go away. In order to do that, it shifts to the left. That's Le Chatelier's principle. So you add and it shifts. Add and it shifts. Now if we look at the volume, okay, so this is gases. Well, volume, that takes us back to the ideal gas law. Okay, so that's PV equals nRT. And we can see here, pressure and volume are inversely related. So if we look, PV equals nRT, if you change the volume, that's basically saying you're changing the pressure. And specifically, they're opposite. So if you decrease the volume, volume goes down, what you're actually saying is you're increasing the pressure. Okay, if you decrease the pressure, you'd be increasing the volume. So this one's a little more complicated. We're not just saying reactants products, left or right. You have to think about the number of moles of gas in the chemical equation. So if there's 2 moles on the left, 1 mole on the right, you have to know that right away. So what's going to happen here is that the reducing the volume of a gaseous reaction mixture shifts that will decrease the number of moles of gas. Okay, so reduce, so lower volume decreases the number of moles of gas. So let's look at an example of that. Here, decrease in volume. This is movable piston. It shows a decrease in volume. And we can see we have 1, 3, that's 4 moles of gas on the left, 2 moles of gas on the right. So if you have a decrease in volume, that goes to the right with the fewer moles of gas. However, I want you to think about this in terms of pressure as well. Decrease in volume, increase in pressure. Okay, so that's changing the pressure. Okay, you decrease the volume, increase the pressure. The pressure, all of these moles are colliding more and forming these moles over here. So in this case, we're increasing the volume, decreasing the pressure. So you have a lot more room for these moles of gas. There's not as many collisions because decrease in pressure, that shifts left, more moles of gas. So that's reactant product, and now pressure. The last one, remember, why does this one stand out? The temperature change changes the value in K. Okay, so that's a big deal. So what we need to know about is the heat of the reaction. This was in one of our previous chapters. It kind of just got slid in there, but this is delta H, or the enthalpy of this reaction. And the key, though, was, is it negative exothermic or is it positive endothermic? So that's the exo-endo piece. What I encourage you to do is write right in there heat. If you know it's endo, heat's a reactant. If you know it's exo, heat's a product. And Le Chatelier's, we just treat it as a reactant or product. If you've written it in, if heat is a reactant, you add heat, that shifts to the right. If heat is a product, you add heat, it shifts to the left. So let's take a look at an example of that. Okay, so this is an exothermic reaction. What that tells us is we can just write in that heat is a product. Okay, so if we cool temperatures, that means we're decreasing the heat, then we have a shift to the left. Warm temperatures cause a shift to the right. Okay, so this is the reaction N2O4 to 2NO2. So cool temperatures, cool, then it goes to this N2O4, and NO2 goes to the heat. So take a look here at this example and see what you can come up with. What I encourage you to think about is, right away, what does delta H mean? If it's endothermic or exothermic. And then if you look at it, think about NH3 being removed, or what if NH3 is added? How's that going to shift equilibrium? And the reaction vessel opened. What does that mean? This is actually asking about volume. Okay, so a change in volume. What's that going to do? And the reaction vessel is cooled, so then that goes back to, is it endothermic or exothermic? So go ahead and go for this one. And what we see here, ammonia, if you take away ammonia, so you remove it, take it away, you got to fill up that void, reaction shifts to the right. Okay, if the reaction vessel is open, so that's volume, well, that means we've got to think about number of moles of gas, and in this case we've got more moles of gas on the left, so that's shifting to the left. Volume increase goes to the greater moles of gas. And exothermic, negative 46, and you can see here, if it's exothermic, it is releasing heat, and again it's cooling it. So if it's exothermic, you're taking the heat down, decrease the heat, that shifts to the right as well. So this is finishing off equilibrium. If you got questions, come see me during office hours.